Okay, and perhaps it'd be a good time to start. Well, first of all, thank you very much for joining the webinar on agricultural and food systems resilience, increasing capacity and advising policy. So before we dive into the seminar, just a couple of points on Zoom. So if you could, it would be wonderful if you could ask your questions in the Q&A function in Zoom, which is probably next to the chat button. And the chair, who's myself, will respond to those. And secondly, just to say that the session is being recorded. Okay, thanks very much. I'm Chetan Deva. I'll be chairing this session. I'm a researcher on crop breeding in future climates at the University of Leeds. So this session will be on agricultural and food systems resilience. And I'd like to welcome you to our joint webinar held in partnership by the AFRICAP project and the Global Food and Environment Institute at the University of Leeds. So AFRICAP's a major international program that aims to make agriculture and food production in sub-Saharan Africa more productive, sustainable, and resilient to climate change. We work in partnerships with local organizations and governments in 4 focal countries. That's Malawi, South Africa, Tanzania, and Zambia. And the idea is to create evidence base to support new country-specific policies. So here's a bit more about AFRICAP. So AFRICAP aims to help countries reduce poverty and hunger, improving livelihood and economic development, whilst addressing the broader aims of the United Nations Sustainable Development Goals. So this diagram here highlights the project structure and 4 cross-cutting themes: farming systems, climate smart development pathways, policy design, and implementation and training capacity building. AFRICAP is led by the University of Leeds and is funded by the UK Research and Innovation Global Challenges Research Fund. So I'd also like to mention the Global Food and Environment Institute, which is an interdisciplinary research institute working to achieve a different global food system. One that works with the planet and provides everybody access to safe and nutritious food. So the aim of GFEI is to develop enduring solutions that facilitate transformative change to create a food system which is socially just, climate smart, and goes beyond sustainability. A food system that can adapt vigorously to enhance the future habitability of the Earth. With that, it gives me great pleasure to introduce our panelists for today. So we have Justify Shava, who's the head of the Southern African Development Community, SADC, Plant Genetic Resources Center, based in Lusaka, in the Republic of Zambia, where he coordinates the promotion of conservation and sustainable utilization of plant genetic resources for food and agriculture in 16 SADC member states. Our second panelist is Dr. Stephen Whitfield, who's an associate professor at the University of Leeds, an associate director of the Global Food and Environment Institute, and the Zambia country coordinator for the AFRICAP program. He's directly involved in research on climate resilient seed systems, the diffusion and adoption of agricultural innovations, and conservation agriculture. Stephen also leads related research projects on agricultural climate services and on agriculture and food system transformation and justice. Finally, I'd like to introduce Dr. Sarah Chapman, who's a research fellow within the Institute for Climate and Atmospheric Sciences, ICAS, at the University of Leeds. For the GCRF-AFRICAP project, she's working on climate change in agriculture in East Africa, using a convection permitting model applied to present day and future climates. So thank you very much. And without further ado, I'll hand over to Justify.
Thank you very much, MC. I'm loading my presentation. It's a short one. Oh, can you see my presentation? Hello, can you confirm that my screen is visible?
Yeah, we can see it.
Yes, I can see it.
Okay, thank you very much. My name is Justify Shava, and I am with the SADC Plant Genetic Resources Center here in Lusaka, Zambia. I'm going to give you a brief talk on the topic here, which is cascading with what has been given as the theme of this webinar: crop breeding for climate resilience in Southern Africa. And I want to look at securing the much needed variation for posterity. So this is how my talk is structured. I'll give a brief talk on the background to, climate change in relation to conservation of our plant genetic resources. And of course, I will talk about a bit of the link between crop diversity and the crop and nutrition security. I will explain the link between SPGRC and the fight against climate change. Then just to highlight some gaps and areas of possible collaboration with any of us around here. I've given here my first slide is climate change from Terra firma to Terra incognita. And here I'm just trying to highlight that even those who doubted that really climate change is around are now beginning to believe that we now have climate change. If you recall, in the 1950s to the 1970s, there were steady gains in crop improvement, mainly driven by research and plant breeding. And we thought everything was all well. And this resulted in constant increase in crop yields. In Southern Africa, some countries actually had what they called 10-ton, 15-ton, and 18-ton clubs, especially in maize breeding, because people were very much elated with the gains that had been recorded in the area of crop improvement. But come the 1980s, we realized that surely there was something that was going wrong in the area of climate change. We began to witness high frequencies of droughts, high frequencies of flooding, new crop pests, and diseases started giving us problems in the farming communities. And what was evident was that these high-yielding varieties had actually lost a bit of adaptation to the new environment that has been ushered in by climate change. So, yes, we had high-performing varieties which were genetically uniform, but the problem was that these new varieties made farmers to blanketly move and abruptly shift into these varieties, and neglecting, the local varieties which are locally adapted to the growing conditions. So in brief, we had lost a genetic diversity with the varieties, the hybrids that we were growing. It meant that these varieties were now vulnerable to the slightest shifts in the growing environment, like the instances that I highlighted earlier on. So we also witnessed that even within our communities in Southern Africa, there were changes in food preferences. People moving away from the indigenous crop varieties, and no one really was taking care of these indigenous crop varieties. So in the end, there was a threat to the diversity that naturally existed in the crop environment, And we were actually threatened by this lack of diversity in future crop breeding programs. So from 1989, the SADC member states worked with the Nordic donor countries to establish the SADC Plant Genetic Resources Center, and its purpose is mainly to coordinate and promote the conservation and sustainable utilization of plant genetic resources in the region. So in brief, we could say that it was meant to be, or it's meant to be, a shield against genetic erosion, especially in the face of climate change. We wanted to come up with an institution where all the plant genetic material of the region can be conserved, and the researchers, especially in the area of crop improvement, can find somewhere from which they can get plant genetic material for use in their breeding programs. That's how this SPGRC was formed. So the SPGRC is actually an institution that was formed by member states from the southern part of Africa, the 16 member states of the Southern Africa Development Community. These are the countries illustrated there. And the center there in Lusaka, Zambia. The center works by collecting plant genetic resources from the member states, looking after them or conserving them centrally in a regional gene bank. That's an ex situ arrangement. The same material that has been duplicated by member states at the SADC Plant Genetic Resources Center is also duplicated at the Svalbard Global Seed Vault in the Svalbard Archipelago in Longyearbyen. We hope that it will be conserved there forever. In case there is disaster in our region, we should be able to retrieve that material and make it available to our researchers to make sure that they can fight against the challenges of climate change that are facing us. So the program is structured in this way. We have an in situ conservation unit that coordinates in situ conservation programs in the region. There is an ex situ unit that is mainly resident at the center in Lusaka, Zambia, and a documentation and information unit whose purpose is to make sure that all the information generated about the plant genetic resources is actually preserved and made available to the users. So what we have achieved so far is we have managed to collect over 62,000 accessions of over 32 species of plant species that are used in the region as a source of food. And of these 18,000 species have actually been, 18,000 accessions rather, have actually been duplicated at the regional gene bank, and we are keeping them here in situ as seeds. Ex situ in the gene bank as seed. We also developed the regional SPGRC documentation and information system, where information about all the accessions that are being held is also stored. It's a network, and all the information about member states and their plant genetic resources is stored here. And of this material, 8,000 have now been duplicated at the Svalbard Global Seed Vault. And our target is that in the next 2 years, all the material which is at the SPGRC can be duplicated at the Global Seed Vault. So these are some of the partners that we work with. The Svalbard, the Crop Trust, Biodiversity, and we are working with the University of Birmingham, the International Treaty, and FAO to ensure that all the material that we have in the region is conserved as a precaution against climate change. So these are some of the areas that we can collaborate if there are any partners who are willing to work with the SADC region in the area of waterproofing the region against climate change by conservation of plant genetic resources. Accession collection, we still think that there is material in the farming communities that can be collected and still be used. by the researchers in variety improvement. The material still needs to be characterized and documented. We still have a long way to go, as we have done not much in terms of finding good characters of the material that we are using or that we are keeping, so that it can be better utilizable. We need also to look at the nutrition content of the material that we are keeping, especially now that we have COVID-19. We think that some of the material that we are keeping could be very useful as natural remedies to the challenge of COVID-19 that we have, in addition to other nutritional benefits to human beings. So in this area, we can collaborate and come up with something that is useful for the whole world of the material from the Southern African part. So that's what I had for you. Thank you very much.
Great, thanks so much for that, Justify. Just allow me a second to share my screen now. Hopefully that's projecting. Yeah, thanks, Justify, for that. A really kind of interesting and kind of impressive overview of just the wealth of resources and kind of basic material that is there for breeding for climate resilience, amongst other things. And that's what we want to focus on really in this seminar. Like, how do you go about breeding for climate resilience and kind of making the most of that wealth of kind of basic material that's already there. So as Chethan has already said, I'm Stephen Whitfield. I'm an associate professor at the University of Leeds. And along with Sarah, I'm going to be presenting some of the work that we have done within the AFRICAP project on climate information for seed system resilience. And we've particularly been thinking about some of the ways in which medium and long-term climate projections can inform the direction of and activities within seed systems in order to build climate resilience. And so we're going to be drawing on analysis that we've done from across the SADC region of both current crop breeding activity and future climate change projections. I'm going to be drawing on two key research outputs. Briefly, on a paper that was led by Andy Challoner at Leeds a few years ago and published in Nature Climate Change, in which we argued that current warming will reduce yields unless maize breeding and seed systems adapt. And I'm then going to draw more substantively on a paper that's due to come out in Climatic Change in the coming weeks, which explores assumptions in crop breeding for climate resilience. This is coming out as an open access paper, and we hope to circulate a link to everyone that's registered for today's webinar as soon as that paper's in print. So as I mentioned, the origins of this work were in a piece of analysis that we did 5 years ago now. And in this work, we characterized the processes involved in identifying target traits for crop breeding, selecting germplasm, crossing, evaluating, testing, regulating, marketing, and then the eventual adoption of new, improved, in this case, maize varieties. And we looked at those processes across a variety of African countries. It's not easy to kind of see that as a single linear process, and perhaps even less easy to put a specific timeline on it. But in the paper, we suggest that that full process can take up to 30 years to complete, from initial conception through to seeing improved varieties in farmers' fields. We then looked at how climates are projected to change over these kind of timescales. And we found that for a large part of sub-Saharan Africa, there's projected to be very significant change in warming at those timescales. Significant in that the projected trend in warming is likely to exceed the amount of variability that's in that signal. So we make the point that the initial conditions under which crop developers are identifying priority traits, selecting germplasm and testing new varieties are not the same conditions under which those seeds will eventually be planted by farmers. So in the context of these kind of quite quickly moving goalposts, we wanted to think about what does a climate resilient seed system look like? Before we get into that, I wanted to just explain how we're defining or how we're thinking about the seed system. And we're doing that quite broadly. We see the seed system as a complex assemblage of actors and processes, flows of information, knowledge and resources, and regulation. And we recognize that these are systems that cross scales, that cross public and private domains, that are differently associated with formal and informal governance. But what kind of holds this diversity of actors and contexts together is that they all contribute towards the development and uptake of crop varieties. And while within the paper that I'm presenting today, we're predominantly focusing on fairly conventional formal crop breeding. We do that with a recognition that there are drivers, stakeholders, and priorities across the system that influence what crops and traits are being bred for. The SADC context is an interesting one to think about. Across the region, a lot of formal breeding takes place through partnerships between national agricultural research systems, international research centres, particularly the CGIR centres, and the private sector is often also involved. And in the SADC region, this breeding is also taking place in the context of a relatively recent harmonisation of seed regulation across the region. And that kind of harmonisation of regulation is helping to create opportunities for the transfer of material and knowledge and information across the diverse conditions that exist across the SADC region. In 2013, Sean Maguire and Louise Sperling published a paper in which they argued that the characteristics of a resilient seed system are multiple, but they are that it's comprised of a diversity of crops, varieties and supply chains, that it has temporal breadth and is planned with long-term foresight, that there's a flow of information and evidence base that informs technology development, that there are effective mechanisms for information sharing and feedback, that they have flexibility, and that their governance and priorities are informed by a careful weighing up of the trade-offs and risks associated with any given breeding strategy. And we start our work with the assumption that climate information, and particularly medium to long-term projections of climate that go beyond those 30-year timescales that we associate with the whole breeding cycle, that those projections and that climate information could contribute directly to enhancing many of these characteristics, particularly where I've highlighted in red text on this slide. And in recent years, others have argued have made a similar argument, authors such as Atlin and Terra, and particularly recently the CCAF's breeding foresight workshops, which have highlighted really the underutilised potential for collaboration between climate impact modelling and crop breeding. So with that said, the aims of our work specifically were to characterise existing activity in the area of crop breeding for climate resilience within the SADC region, to illustrate some of the ways in which climate model analysis can contribute towards an evidence base associated with these existing strategies and existing activity, and to make recommendations about the integration of climate information within seed systems more broadly. The way we went about this was firstly to develop an online survey, a survey which we disseminated to African seed system stakeholders. And the survey asked respondents about the priority crops and traits that they work with, the extent to which they use climate information at different temporal scales, and what they perceive as bottlenecks in building seed system resilience. The survey received 238 responses, although the results that I present or that I'm focusing on here are a subset of those that came from stakeholders based in Southern Africa, of which there were 145 responses. And we supplemented that survey with a review of grey and academic literature. We then used Cordex ensemble climate models to evaluate some of the trends in key crops and traits that emerged from the survey. And Sarah will say a bit more about those methods when I hand over to her in a few minutes. Before that, I wanted to quickly summarise some of the results that came out of that survey. A perhaps unsurprising outcome was that maize is the dominant focal crop for research. And that's reflected in maize having the highest turnover of new varieties. However, it doesn't predominate in our survey quite to the extent that it did in the DIVA database of varietal release that was put together 10 years ago. And that might suggest that there is increasing attention being paid to non-maize crops, a point that was supported by some of the open-ended responses that we received in the survey. Another finding was that of the climate stress related traits, which include things like resistance to heat stress, resilience to flooding and more, that were being bred for, most effort was being put towards two traits in particular, those being early maturity of crops and tolerance to mid-season dry spells. Although these, it's worth pointing out that these climate stress traits didn't necessarily come out as any more important than a whole host of non-climate related traits like nutritional properties or resistance to pests and disease. Of the major CGIR initiatives in the region, I just picked out a few on this slide. So CIMMYT, for example, are leading work on insect resistance and drought tolerance in maize. IITA on insect and disease resistance in a whole variety of crops. And Harvest Plus on improving vitamin A and zinc in maize, amongst a variety of other initiatives. when it comes to use of climate information, we found that there wasn't a big difference in the extent to which climate information is used by those at different stages of the breeding, testing, and marketing ends of the seed supply chain. But there is quite a strong bias towards the use of shorter term or historical climate data to inform activities, with less access to and use of climate projections with a 5 to 20 or a 20-year plus time horizon. And we didn't find any concrete examples of how specific long-term climate projections had influenced the choice of breeding materials or target traits within crop breeding programs. So that broad characterization of seed system activity kind of set the scene for the analysis that we went on to do. And for this, we picked 3 illustrative crop strategies that we had identified within current activity. And we tried to think about how climate information can be used to help interrogate the assumptions that underpin breeding for climate stress. I'm going to hand over to Sarah at this point to give us an overview of some of that climate analysis work. So over to you, Sarah.
Thank you, Stephen. I'll just share my screen. Okay, so hopefully everyone can now see my slides. So I'm going to talk about the climate analysis we did for this project, and we focused on 3 main things. The first thing was we wanted to test whether the climate projections were supporting a shift to early maturing varieties. And we did this by looking at how the rainy season was changing and looking at growing degree days. And for those of you not familiar with this concept, growing degree days are a measure of heat accumulation by the plant, and they measure how long it takes for the plant to reach maturity. Another thing we looked at was change in dryness during the rainy season, and the final thing was change in cassava toxicity, and I'll explain a little bit more about what I mean by that when I get to that section. And to look at all of these things, we use the Cortex Ensemble of Regional Climate Models. This is a set of 23 models for Africa, and we use the RCP 8.5, which is a high emission climate change scenario, and RCP 4.5, which is a middle of the road climate change scenario. And we also looked at the middle of the century and the end of the century. I won't go into too much more detail on the methods for all of this, but if anyone has any more questions, please feel free to ask me at the end. Okay, there we go. So the first thing we looked at was whether the climate projections are supporting a shift to early maturing varieties of crops. So to do this, we looked at how the length of the rainy season was changing with climate change and how the number of growing degree days accumulated during the rainy season was changing. So we looked at short, medium, and long duration crops, which were defined as needing to accumulate 500, 1,000, and 1,500 growing degree days before they reached maturity. So that's what this figure here is showing. The first plot is showing the present day, and it is showing where those short, medium, and long duration crops are able to reach maturity within the rainy season in the majority of years and in the majority of models. The second column is showing the situation in the middle of the century, and the third column is showing the end of the century. And the first row is showing RCP 8.5, which is a high emission scenario, and the second row is showing the RCP 4.5 scenario. So what these models are showing in the present day is that the majority of the area that is suitable for growing crops is only suitable for the short duration crops, and there's a very small area where the long duration crops are able to reach maturity within the rainy season. The situation changes by the middle of the century, however, particularly for RCP 8.5. So in this scenario, you can see that the area that is suitable for growing crops for growing the short duration crops has expanded, and the area that is suitable for the long and medium duration crops has also expanded. And the main reason for this is that at this point in time, the length of the rainy season hasn't changed much, but it has gotten hotter, so more growing degree days are accumulated during the rainy season. So the crops are able to mature faster because of the higher temperatures. By the end of the century, the situation has started to reverse a bit, particularly for RCP 8.5, and you can see the area that is suitable for growing crops has started to contract again, and this is because at this point, the length of the rainy season has started to decline. However, there is a large amount of uncertainty associated with these results. So for this set of climate models, the Codex Ensemble, when we talk about temperature, there's a lot of agreement among the models. All of the models are agreeing it will get warmer with climate change. But when we talk about rainfall and rainy season characteristics, there is more disagreement among the models. And that's what this figure here is showing. So this is showing the change in the length of the rainy season over time. The solid line is showing the mean across all of the models, and the shading is showing the variation amongst the models. So if you look at the middle of a century, at this point in time, there is a little bit of a decrease in the length of the rainy season, but there isn't that much change. But there's a lot of variation amongst the models, and we have some models showing the rainy season could increase, while others are showing it could decrease. By the end of the century, more models are showing the rainy season should get shorter, particularly for RCP 8.5. But again, we still have a large amount of disagreement amongst the models, and we still have some models showing that even at this point, the rainy season could actually increase. So when it comes to things like temperature, there's a lot of agreement amongst the models, but for things like rainfall, it's a bit more complicated and there is more disagreement and uncertainty. So the next thing we looked at was dryness. So first we looked at dryness over the entire year, measured by the consecutive number of dry days. So this first column is showing the mean maximum consecutive number of dry days per year. And then the second and third columns are showing how that changes with climate change. So you can see that over the entire study area, it's getting drier, and it's getting drier more by the end of the century and for RCP 8.5. And this could mean either that the length of the dry season is increasing or that the dry season is getting drier. So there are fewer rain events within the dry season. We also looked at this specifically for the rainy season. So this first column is showing the percentage of days in the rainy season that are dry. So in the present day, for most of the northern parts of the study area, between 20 to 40% of days within the rainy season are dry, and this increases in the more southerly parts of the study area. And then the second and third columns are showing how that changes with climate change. So in most areas, it is getting drier during the rainy season, but not everywhere. So parts of northern Tanzania, it's getting wetter during the rainy season, but for most of the study area, it is getting drier. And this could mean that the rainfall is becoming less frequent, but more intense during the rainy season. So as I mentioned before, there is a large amount of uncertainty when it comes to rainfall with climate change. However, less frequent and more intense rainfall is a fairly common finding of climate projections globally, not just in Africa. So the last thing I'm going to talk about is cassava toxicity. I'll just give a little bit of background on what I mean by that before talking about what we did. So cassava contains cyanogenic compounds, and when the plant is damaged, for example, by eating it, these compounds are released and cyanide is formed. Now, different varieties of cassava have different amounts of the cyanogenic compounds. Sweet varieties have less, and they require less processing to be made safe to eat, but bitter varieties have more cyanide in them, and they require lengthier processing techniques to be made safe to eat. Now, the World Health Organization guidelines for cassava products are about 10 parts per million of cyanide for it to be safe to eat. And if you start with a cassava tuber that has about 300 to 400 parts per million of cyanide, with ideal processing, you could probably meet that safe guideline. So what does this have to do with climate change? Climate change could potentially increase cyanide concentrations as the cyanide content in cassava is increased by drought and by high temperatures. So in Tanzania, in normal climate years, the cyanide content in cassava tubers is between about 100 and 200 parts per million, but values between 300 and 800 parts per million have been found in drought years. So we wanted to have a look to see whether conditions for high cyanide content in cassava would change with climate change. So drought on its own can increase the cyanide content in cassava tubers by up to 4 times, and high temperatures combined with drought can increase the cyanide content by 6 to 7 times. The plant does have some capacity to recover if it's harvested during a wet period, but the cyanide content is still higher than if the plant had never experienced a drought. So we wanted to see if the conditions that led to higher cyanide content changed with climate change. So we did this by looking at drought and high temperatures. And this is the first part of that. This is drought measured by the Standardized Precipitation and Evapotranspiration Index. That first column is showing the total number of months that count as a drought month. The second column is showing, and the second and third columns are showing how that changes with climate change. And these values are the number of drought months over the entire 20-year study period. So in the present day, that's showing that droughts are occurring maybe 0 to 2 times per year. But droughts are increasing by mid-century in both RCP 8.5 and 4.5 across the entire study area, and by the end of the century in RCP 8.5, droughts are more common everywhere, and most months in the year would actually count as being a drought month. And as a reminder, droughts on their own are enough to increase cyanide concentrations in cassava by up to 4 times. So we also looked at hot months. These were defined as a monthly mean minimum temperature above 25 degrees C and maximum above 38 degrees C. So that first column is showing the situation in the present day, and that's the total number of months that meet that threshold over the entire study period. And you can see in the present day, it's very rare. These conditions are less than a yearly occurrence. By the mid-century, which is the second column, these conditions are still very rare, but they are starting to become more frequent by the end of the century for RCP 8.5. And then we combined all of this. So we looked at where droughts occurred with a hot month. And in the present day and in the mid-century, again, these conditions are quite rare, mostly because the conditions for the thresholds for being a hot month aren't met. So in the present day and the mid-century, these conditions aren't happening on a yearly basis. But by the end of the century for RCP 8.5, those red areas are where you might be getting one of these hot months with a drought occurring once a year. And these conditions are where cyanide concentrations could potentially increase by 6 to 7 times. So I'll just leave it and stop there on that note and pass it back to Stephen.
Thanks, Sarah. Let me get my screen back up. Okay. So, I wanted to draw on some of the examples that Sarah has outlined, which we see as being illustrative of some of the kinds of useful climate analysis that could be done rather than necessarily being exhaustive of those kind of possibilities. And I want to summarize some of our ideas about the potential opportunities for bringing together this kind of climate analysis with crop breeding efforts. And we identify in our papers some ways in which these projections of climate trends and variability can contribute to what Maguire and Sperling might describe as an informed weighing up of the trade-offs and risks of crop breeding strategies. So the first of those ways is in understanding changing durations. By using climate models, for example, to identify at what point in time the prevailing climate conditions will more frequently favour a long duration variety or crop over a short duration one for a given location. and therefore speak to the relative benefits and costs of breeding for early maturity, one of the kind of target traits that we noted from our survey. The second is in understanding what the critical constraints on productivity and quality for any given crop is likely to be into the future. By identifying what climate thresholds might have the most significant effect on the viability and quality of those particular crops. Now, this might not be a yield constraint necessarily, but could be a quality constraint. We've briefly discussed how cassava is seen as an increasingly viable crop in terms of its productivity under hotter, drier climates, but have also shown how this could potentially be associated with crossing critical thresholds in toxicity, which might be something that breeders want to focus on in terms of traits of different cassava varieties. The third is in understanding and helping to target breeding and testing conditions. By identifying significant changes in agroclimatic conditions over the timescales that we talked about for breeding and delivery and adoption of new seeds, models can help to indicate where, for example, artificial environments such as a greenhouse or analog environments, those being locations elsewhere which today's climate is representative of the climate that we might want to breed for in the future, where those analog environments might be useful for variety testing. And in the context of the regulation, the kind of harmonization of seed regulation across SADC, it might be particularly useful for helping to identify where there are varieties or germplasm for one part of the region that may in the future be useful in another as the climate shifts. The fourth application is in understanding crop selection options. So by identifying transitions into and out of the suitability window for different crops, understanding where one crop is likely to become marginal or unviable and where another crop might become relatively more suitable, and using this as a basis for understanding in which crops resources and effort might be invested when it comes to breeding. And in many cases, this might be pointing to appropriate alternatives to maize. We believe that it's useful to see climate information as a part of a wider integrated exchange of information. So whilst climate information can be used to inform discussions about which crops and traits may be climate resilient, it's only really useful if, on the one hand, we're asking the right questions of models, and on the other, that the limitations of models, what they can and can't tell us, are understood. And for that, it's important that there is shared learning across those involved in crop breeding, with those involved in farming and in seed marketing and extension, and those involved in climate science and services. We know, for example, that a lot of breeding effort is not driven by climate risks, but by other priorities, such as nutrition, diversity, consumer and market demand. And it may not be useful to use models simply to look for optimal crops based on their climate suitability, because there could be multifaceted other reasons why investment would not be put into the development of those crops. And so a shared kind of dialogue could help to both identify the specific ways in which climate information can contribute to the weighing up of specific crop breeding options, And it can also help to ensure that the outputs of climate models are correctly interpreted. A key kind of aspect of that interpretation, of course, is understanding that there are assumptions within models and uncertainty within climate model projections. So that where climate information is feeding into breeding decisions, that kind of uncertainty is not misrepresented. And we think there's a responsibility here for climate modelers, not only to use ensembles of models and to evaluate sensitivity in their assumptions. And Sarah's mentioned some of the ways in which we try to do that in the paper, but also to communicate these very clearly. So just in summary, we've argued that breeding for climate resilience currently focuses on a relatively narrow range of crops and traits, and that there's a time lag that means that conditions for commercial growing may be significantly different to those under which germplasm is selected and varieties are crossed and tested. We've argued that climate model projections can help to interrogate breeding options and provide a stronger and more nuanced evidence base for resilient crop breeding. But that, on the other hand, that climate information isn't enough in itself. It should form part of an integrated knowledge and information system, and uncertainty within that information must be communicated clearly if it's to be informative and effective. Before I hand back over to Justify for some of his reflections on what we've presented, and then we open up for comments and questions more broadly, I want to just highlight that through the AFRICAP programme, we're planning to run an online open dialogue event in March, Monday the 15th of March. And this dialogue is going to be focusing on this question of what is a climate resilient seed system and how can it be achieved? Our intention is that dialogue is going to form part of the ongoing global open dialogue process that's feeding into the UN's Food Systems Summit towards the end of the year. And the event will follow the Food Systems Summit dialogue format and be reported back to the relevant action tracks of the summit. We're going to circulate details of that dialogue event to everyone that's registered for this webinar, and we very much hope that you'll be able to join us for that, for hopefully an open, engaging and interactive discussion on this important and multifaceted question that we've only really just kind of touched on one aspect of in today's presentation. So Justify, with that, let me pass back over to you for your thoughts and reflections before we open up to the audience questions.
Thank you very much, Steve. And thank you very much, Sarah, for your elaborate and quite informative presentation about the findings on your study, which you carried out in Southern Africa. From the presentations that you have given us, I'll start with Steve. It can be seen that indeed in Southern Africa, the seed system is quite an extensive system that starts with a variety selection, goes to breeding, multiplication of varieties, going as far as the distribution and the use of the varieties. But what has come out from the study and the presentation by Steve is that in Southern Africa, it looks like there is not much use of climate information in the development of the varieties that are climate resilient. And the indications are that the main, mostly studied crop varieties are mainly from the maize species, and the others are not really well tackled, despite the fact that climate resilience itself requires that there be a lot of diversity in the varieties involved, as well as the crop species that are involved. So in brief, you pointed out that the characteristics of a resilient system should be that there should be diversity in terms of species and varieties involved, and also that the intervention in trying to come up with climate resilient crop species and varieties should be timeous enough to give us the benefits that are expected. When it comes to the issue of the use of the available information, Sarah also gave us an indication that available information indicates that indeed there is climate change taking place within the Southern Africa. And this is actually evidenced in the number of rains, number of days, or the length of the days, the length of the season in terms of number of days each season has. There is also an increase in the dryness of the environment, as well as a general change in the toxicity of crops like cassava, as an indicator that maybe the high temperatures and the dry conditions are promoting the production of more cyanide. Generally, this was evidence compared to what was happening in the past seasons. Over the past century, as indicated by the codex. So, the take-home message here is that surely it's very, very important that we use climate information to help us come up with the systems that give resilience to climate change. And the climate information, if used well, should be able to indicate duration changes in the growing season of crops. It must also be able to show us the changes in the productivity as well as the quality of the crops that we are growing in the region, and help breeders to come up with the varieties that are well adapted to the environment that has been ushered in by climate change, and through proper breeding, use of proper breeding methods, as well as a good selection of testing environments for these varieties. And this will eventually lead to good crop selection. So, in summary, we can say that climate information is part of a broad system that is very much important in the development of climate resilience within the Southern African region, and it must be used quite extensively in development of varieties through use of broad germplasm that is available in the region. In brief, that's the take-home message that we can get from the presentation that have been given by Sarah, and Steve complemented by the brief remarks that I gave at the beginning of this webinar. I hand over to you to give for your final remarks.
Okay, thank you very much to all the presenters. I think we'll now move to questions from the audience. So as I said, there's a question and answer, a kind of Q&A chat. So if you have any questions, please enter them there. And I see there's already quite a lot of questions. So so I'll start by reading reading a few of those. So the first one, this is a question to you, Justify, is, I think the question is, are all the materials conserved in SPGRC for both animal feeding or forage and human food?
If I got the question correctly, the listener wants to hear if the material that is conserved at the SPGRC is for forage or human consumption. And the main objective of our conservation efforts is to ensure that the material we have is used for human consumption, breeding for human consumption, but there is no limitation to the use to which the material can be put. Those who want to use it for forage or directly, or forage in terms of germplasm foundation used in development varieties for forage, there's no limitation at all. It's all allowed.
Thank you.
Over to you.
Thank you. And I think we have a second following question for Justify, which is, how are you conducting the sensitization of the effects of climate change, and how can small-scale farmers access the preserved materials you have at your center?
Thank you. Well, our sensitization program goes like this. Because we're a regional center that works as the hub and spokes model, where we also have centers in member states, certain member states. We use all the possible media, like the radio, like even the websites, and even other public platforms like agricultural shows. We talk of farmers clubs, in any other gathering that has anything to do with agriculture, to present information about conservation of plant genetic resources. So that's how the information goes to the farmers. And when it comes to ensuring that the farmers access the seed, because we have centers in member states, the centers in member states make sure that they communicate to all farmers about the seeds that are being collected each and every time, and the availability of those seeds for them to use in whatever programs which they want. So using national broadcasting services in most cases, as well as national newspapers in the region, information about conservation and the availability of the material conserved is given to farmers. I hope I've answered the question.
Thank you. I'll just move to the next question, which is for Stephen Whitfield. So the question is, have you conducted research on how drought tolerant and profitable crops like sorghum, which are not so popular, can be introduced to replace the maize that's widely accepted in the Southern African region?
Yeah, okay, thanks for the question. So not within the context of the paper that we presented today, which was just for which we just kind of picked out a few examples of climate impacts projections. But for that, I would perhaps point the audience member to some of the broader work that we've been doing within the AFRICAP program. And a large kind of focus of that work has been on using integrated and multi-crop modelling tools to look at how climate change is affecting suitability and optimality for a variety of crops across, particularly our focal countries, so Malawi, Zambia, Tanzania and South Africa. And I think in all four of those countries, sorghum has been included within that analysis for exactly the reasons why, exactly the reasons suggested in the question, that there is potential advantages in terms of resilience and nutrition for a crop like sorghum as a maize alternative. So just to say that kind of, if you're following the AFRICAP program, that work is forthcoming, and you'll be seeing kind of more of the outputs of that analysis over the coming months.
Thanks, Stephen. So the next question's for all of the panelists, or anyone who would like to answer. So the question is there any understanding between crop breeding systems in conjunction with soil properties in line with climate information?
Yeah, I mean, if I'm kind of interpreting the question correctly, obviously the kind of interaction between climate, crop, soils, and a variety of other variables is really important. And that's why the potential for kind of modelling to inform breeding is not just straight climate models, but is also potentially climate impacts models, climate models combined with crop models that can kind of capture more of those interacting variables. And so I think that's a good point to kind of look for ways to use modelling tools and different sources of information to consider not just those direct climate crop interactions, but also the other important variables like soils that mediate that relationship. And again, we're doing some of that work using crop models within the AFRICAP program. So again, there'll be kind of work forthcoming that presents some of that analysis.
Okay, thanks, Stephen. I'll leave a pause in case any of the panelists would like to add to that. Otherwise, I'll carry on with the questions. We've got loads of questions, actually. This is great. So the next one is, should climate risk the question is, should climate risk not be a driver of crop breeding in sub-Saharan Africa now, given the threats of increased droughts and high temperatures highlighted by the climate models? So that's to any of the panelists who'd like to answer.
Yeah, I mean, I think that's exactly the point that we're trying to make, and hopefully communicated relatively clearly in the presentation, that climate change obviously is happening now and is evident in changes in crop suitability and productivity now, but also that there are time lags involved in the breeding process and the development of crops, and those crops getting out into farmers' fields. And so that's why we're arguing that it's so important that we look to what those kind of climate futures are going to be and breed proactively for them now, so that when those improved varieties are out, they're not already outdated.
Okay, on to the next question, which is for Stephen and Sarah. So the question, which I suppose is kind of a comment, is that the focus seems to be on calorific crops. And if you accept that maize and cassava are not necessarily solutions to other sources of nutrients, what would an approach that accepts this position about the attention to other crops such as pulses, fruits and vegetables look like? I'm paraphrasing the question slightly there, but I think that's what they're getting at.
Yeah, I mean, it's a similar point to the question about sorghum. I think the values in looking broadly across a variety of crops, not just for their climate resilience, but also for their nutritional properties and their marketability, and a whole host of other things. Again, I tried to make the point in the presentation that we recognise that climate resilience or kind of tolerance to climate stresses is not the only or necessarily even the most important priority that should inform breeding strategies. And that's why kind of not taking climate information alone, but seeing it as part of that kind of broader information system, I think is so important. And again, I'd kind of point to the broader activity that we're doing within the programme that is looking at some of those future climate impacts on a variety of crops beyond the very narrow focus that we've presented today. And not just at the climate impacts, but also what that then means for nutritional profiles and trade, and all of those things are part of our integrated modelling work, which is driven really by that understanding that you need to look at the system as a whole rather than kind of take kind of individual aspects of it out of context. So yeah, another plug for that work that's going to be coming out, and hopefully speaks to those points and those questions.
Thanks very much, Stephen. So the next question's for Justify. And the question is, you've talked about the need to collect more germplasma in SADC for breeding purposes and also for conservation. And what the question is asking is, how do you do that? Is this a community-based approach where communities can bring in their germplasm, or is it based on the country institutions?
Thank you. The collection approach is combined. The communities are open to bring a germplasm to the gene banks, the national gene banks, or even the regional gene bank. We accept the germplasm. And the institutions also do regular collections annually, where they go to the farming communities and interact with the farmers as they collect germplasm for long-term conservation. They also get information about the characteristics of the germplasm, which they document and upload on the SADC documentation information system. So both approaches are useful, and they are used, especially if the environment permits people to move around and do the collection, like what was happening before COVID-19 came in. Thank you.
Thanks very much. And a following question, which I think is also to Justify. When it comes to testing of the cultivars, do you test them throughout SADC, or does each country test independently?
As of now, we are generally not doing any testing at the regional center. Rather, member states in their own breeding schemes or utilization schemes are the ones that test their material in the respective regions of their countries. Thank you.
Thank you. And the next question is also for Justify. And the question is, from a policy and regulatory angle, SADC adopted in 2008 an agreement on seed harmonization regulation. From your presentation, PGR's conservation of the diversity of neglected varieties seems to be the main path followed by SADC in respect of addressing climate change effects to seed systems and crop improvement in the region. And the question is, can you see the SADC engaging in some sort of regional seed policy development or review that takes into account climate information and services? the kind of information provided by the models and presented by Sarah? Sorry, that's a very long question.
So maybe you reread the question?
Sorry, I'll try and summarize it a little bit better. So can you see the SADC as a whole engaging in some sort of regional seed policy development or review that takes into account climate information of the sort that Sarah was presenting?
Yes, indeed. I think the 2008 seed harmonization regulations or policy that the SADC is trying to put into effect is quite a testimony that the region is actually geared to ensuring that the whole region gets varieties that are climate relevant during this era by making sure that there is actually a seamless movement of seed across the whole region. So, you know, this is SADC is an intergovernmental organization, and you know that intergovernmental organizations work mainly by consensus, though it may take a bit of time for some policies to be put into effect and become operational. But with the kind of experts that have been engaged by the SADC Secretariat, I'm seeing the dream of having policies that ensure that varieties which are climate smart are adopted across the whole region are going to be put in place very soon. Thank you.
Thank you very much. Okay, so the next question is, what is the SADC doing to ensure that the program continues despite the COVID-19 pandemic?
I want to believe that the question is talking about the conservation program. Generally, I would say, as of now, we are still operational. We're still open despite the presence of COVID-19. We are operating at a farm, and that in itself means that we are kind of isolated from the general population, which gives us an advantage that we are able to do our field operations without disturbances. We are also capable of actually processing shipping documents. We are part of the key staff that is allowed to do the minimum operations that ensures that processes go on. And I must also testify that the SADC member states are still funding all the operations. They are providing all the necessary financial support to ensure that all the key operations go on. Of course, despite all these challenges of getting funds in the middle of COVID-19, at least some money is being given to ensure that our processes move on. And we are still optimistic that the support will continue to come, and the things are all up and running right now. Thank you.
Thanks very much. So the next question, I guess this is to Stephen and Sarah, which is, do you take into account genetic information in your models, in the way you do the modeling?
No. My models are much more simple than that. So they're mainly taken in average characteristics across many maize varieties for the region. So no genetic information in them.
Yeah, I mean, Chethan, you could probably kind of answer this even better than I could, but if the question is more in relation to some of the crop modelling that we're doing outside of this work, the crop models don't really kind of directly model kind of molecular or genetic information, but rather they capture like phenological processes that are perhaps different in crops of different genetic makeup. So they're kind of indirectly capturing some of that, but they do that kind of only imperfectly anyway. So that the majority of crop models are not great for kind of distinguishing between varieties, although you can kind of tweak those phenological kind of expressions that you see from different crops to kind of simulate what different properties might look like or different traits.
Thank you. Still a few questions to go. So I guess this next question is really asking, what is the contribution of crop wild relatives, and how do they contribute towards breeding programs? So I guess that's for any of the panelists who'd like to answer.
I would take the question. Yeah, the crop wild relatives are very important, especially in this time that we are being threatened by climate change, because they are sources of potentially novel but well adapted genes that can be introgressed into the material that we are using right now to make them better adapted to the new climatic conditions that are ushering in new pests and diseases, and also making them even more adapted to the drier conditions that we are experiencing right now. I must comment also that it looks like even in Southern Africa, there is not much intake of crop wild relatives in breeding schemes, though we have quite a number of species that can be used. I think we need to do more to ensure that crop wild relatives are also used in coming up with varieties. Thank you.
Thank you very much. And another follow-on question to Justify. So the question is, what methods do you use or are used in breeding programs? Are they conventional or molecular breeding, which I guess might be marker-assisted selection? That might be what they mean. Or is it an application of both generally?
Well, as a conservation scheme or program, we haven't really started doing breeding work, but our sister institutions, the ones we work with, mainly are using the conventional breeding approaches. You know, because of limitations in terms of skills availability, and also the resources to undergo these advanced breeding methods, like use of marker-assisted selection. So we end up going the simple conventional breeding approaches. Though there are some countries like South Africa and some parts of the region, like I think in Zimbabwe, they can still be using marker-assisted selection, but to a very limited extent. Thank you.
Thank you very much.
I'm just noticing that we're getting towards the end of the time. It's a shame to kind of cut short the questions because there's lots of interesting ones coming in, but maybe we could answer some of them offline, some of the remaining questions. Great,
makes sense. In that case, I'd like to say thank you very much to everybody who attended, and of course to the panelists for their talks and for the Q&A session. Just to say that slides and recordings will be shared by email, and also to say that the next AFRICAP seminar is on the 23rd of February, which you can register at the AFRICAP website. So again, Thank you very much for attending and for a fascinating conversation. And we'll wrap up there.
Thanks, Jathan.